Welcome back to The Explainer. Today we're jumping right into episode 8.5, Active and Passive Fire Protection on an FPSO. Let's set the stage here. Picture an FPSO operating, say, 200 kilometers offshore. If a fire breaks out there, it is a literal race against time. I mean, you can't exactly just dial emergency services and wait for the local fire brigade to show up, right? So let's dive into how these massive offshore facilities are actually engineered to survive.
When a fire happens in this kind of extreme offshore environment, you've got a massive floating facility processing highly flammable hydrocarbons. Basically, a brutal, simultaneous conflict starts playing out right there on the deck. On one side, the fire is relentlessly trying to heat up the structural steel. Its main goal? To raise the temperature of that steel until it completely loses its load-bearing capacity, which, as you can guess, would lead to a catastrophic structural collapse. But on the exact same timeline, your fire protection systems are fighting back. They're engineered to counteract that extreme heat, specifically to buy you just enough precious time for operators to safely shut down the process, isolate the hydrocarbons, and get everyone out. It really boils down to this high-stakes race of thermal physics.
So to win that battle, we rely on two entirely different but totally complementary strategies. First up, we have passive fire protection, or PFP. This works purely through the material properties themselves to delay heat transfer and essentially buy us time. The best part about it? It requires absolutely zero activation to work. It's just there. Then, on the flip side, we have active fire protection, or AFP. This actively fights the fire directly using water, foam, or suppression gas. But unlike PFP, this actually requires detection and activation to do its job. The crucial takeaway here is that both of these systems are absolutely mandatory. You need them both, and honestly, neither is sufficient on its own.
Let's zoom in on passive fire protection first. Think of PFP as the built-in armor of the vessel. It uses specialized heat-resisting materials to literally divide the FPSO into distinct, safe fire zones. By setting up these physical boundaries, PFP creates primary fire containment areas that stop the fire from spreading across the deck. And again, this requires zero manual or automatic activation. If a fire flashes, boom, the PFP is already working the very millisecond the heat hits it.
Now, what's genuinely fascinating is exactly how these primary barriers pull this off. First, we have intumescent coatings, which are applied directly to the structural steel. When this brilliant chemical compound is exposed to extreme heat, it actually swells up. It increases its volume, decreases its density, and forms this thick insulating char layer right around the steel. It's like a protective blanket. Then we have SOLAS A-class fire divisions, think steel bulkheads packed with insulation. These are designed to maintain their structural integrity and limit the temperature rise on the unexposed side to just 140 degrees Celsius on average. If you see an A60 rating, that means it gives you exactly 60 minutes of fire resistance under standard cellulosic fire conditions. For even crazier hazards, we step up to an H120 rating, often using a really thick layer of cement-based intumescent coating. H120 gives you a full 120 minutes of protection against intense hydrocarbon fires, and you'll strictly see this used on accommodation boundaries that face those high-risk process areas.
Okay, let's test your engineering intuition for a second. This is quite literally a life or death metric in structural design. At what temperature do you think carbon steel actually begins to lose significant load-bearing capacity in a fire? Is it A, 200 degrees Celsius, B, 400 degrees Celsius, or C, 800 degrees Celsius? Take a quick second to lock in your guess, because this specific threshold is the exact reason all our passive fire protection is engineered the way it is.
Got your answer? The correct one is 400 degrees Celsius. Right at approximately 400 degrees, carbon steel hits a critical failure threshold where it loses roughly 50% of its yield strength. At that point, it is no longer the rigid, load-bearing framework you need it to be to hold up, thousands of tons of heavy topsides equipment.
And this perfectly illustrates why controlling that temperature is so absolutely vital. If that steel hits 550 degrees Celsius, it retains only 30% of its ambient temperature strength. I mean, that is completely insufficient for most structural load cases. The vessel would literally buckle. So the ultimate non-negotiable survival metric for PFP is that it absolutely must keep the structural steel below 400 degrees Celsius for at least 60 minutes. Why 60 minutes? Well, that's our golden hour. That's the exact amount of precious time we need to run an emergency process shutdown, give the active fire suppression systems time to work, and most importantly, get all personnel mustered and safely evacuated into lifeboats.
But while the passive armor is buying us time, we also have to go on the offensive. And that brings us to active fire protection. This encompasses all the systems designed to aggressively suppress and fight a fire directly the moment it's detected. And remember, because there is no external fire brigade rushing in to save the day out in the ocean, these systems have a mandatory requirement of 100% redundancy. If one pump or one single line fails, a complete backup system has to be sitting there ready to instantly take the load. No exceptions.
The absolute beating heart of this active system is the fire-water ring main. Picture this. It's a massive pipe running in a full, continuous loop right around the entire perimeter of the FPSO deck. Because it's a loop, if one section gets blown out by an explosion, you can just isolate it with valves and still feed firewater to the rest of the vessel from the opposite direction. Pretty clever, right? Now, it's fed by a main fire pump that's sized for 100% of the worst-case demand. But remember that redundancy we just talked about? If the ring main pressure drops, a standby pump automatically kicks in. And if the worst happens, say the entire vessel suffers a total blackout and loses main power, an emergency diesel-driven fire pump, which is fully compliant with NFPA 20 standards, starts up automatically. Having complete independence from the main power grid is just a non-negotiable survival feature out there.
Let's ground some of these abstract concepts in rigid engineering realities for a second. Depending on the hazard, we use highly specific application rates. For your open process areas, we use fixed water deluge arrays. When these get triggered, open nozzles simultaneously flood the entire area at a massive 10 to 12 liters per square meter per minute, with 12.2 actually often being the minimum design standard. For crude pool fires, we use fixed foam, applied at about 4 to 6 liters per square meter per minute. And for enclosed spaces, like engine rooms or battery spaces where dumping water would just completely destroy the critical equipment, we use clean agents that provide total flooding of the space. To really wrap your head around the sheer scale of what we're dealing with, let's walk through a worst-case scenario fire-water demand calculation. Unlike those little office sprinklers that pop one by one, an offshore deluge system activates simultaneously across an entire zone. So let's say you have an 800 square meter process zone that needs 10 liters a minute. That is 8,000 liters per minute just for the deluge alone. Add in 2 fire monitors aimed at the hazard, each pulling 1,200 liters a minute, plus your hose reels, and suddenly your total demand skyrockets to somewhere between 11,000 and 15,000 liters per minute. And the pumps must sustain this massive flow while keeping up 7 bar of pressure at the monitors and 3.5 bar at the hydrants for a minimum of 20 to 30 continuous minutes. Honestly, it's an astonishing feat of hydraulic engineering.
Now, when it comes to foam systems, engineers have a very deliberate choice to make. Low expansion foam, which expands at a ratio of 1:1 up to 20:1, is the absolute industry standard for crude pool fires out on the open deck. By mixing a 3 to 6% concentrate of AFFF or fluoroprotein with seawater, it creates this aqueous film that literally floats right on top of the oil. It simultaneously blocks the oxygen and cools the fuel down. High expansion foam, on the other hand, expands up to a massive 1,000:1 ratio. Think of it like a giant bubble avalanche. This is used for total flooding of enclosed, high-hazard spaces like compressor rooms, and it can suffocate a fire in a matter of seconds. For those highly sensitive enclosed machine-of electrical spaces where foam or water would just ruin the equipment, we rely on clean agents like Novec 1230, FM200, or CO2. But we need to pause here for a stark and, quite frankly, grim safety warning. A CO2 total flooding system works by displacing oxygen to put out the fire, but at the 34% concentration required to actually extinguish a fire, CO2 is instantly lethal to humans. Because of this extreme hazard, full evacuation of the space and incredibly loud pre-discharge alarms are absolutely mandatory by international law before the system can ever activate. It is serious business.
So, pulling it all together, offshore safety relies on an integrated survival strategy. It's this perfect marriage of passive barriers and active suppression, all working hand in hand. Your intumescent coatings and A-class walls keep the structural steel safely below 400 degrees Celsius for 60 minutes. Your deluge arrays aggressively flood those open process areas. Your clean agents safely suppress enclosed machinery fires. That incredibly independent, fully redundant fire-water ring main guarantees water is going to flow even in a total vessel blackout. And the whole shebang is carefully choreographed to ensure that every single soul on board has the time to safely evacuate to muster stations and board those lifeboats within the strict 30-minute SOLAS mandate. So we've covered how to survive and suppress a fire once it actually starts. But what if we could design the facility to prevent the ignition from ever happening in the first place? Now that is a fascinating engineering challenge of its own. In our next chapter, we're going to dive into hazardous area classification. We'll explore exactly how zones are defined across the deck and how mapping these flammable atmospheres dictates literally every single electrical and HVAC design choice on the vessel to eliminate ignition sources. It is a completely different side of the safety equation, and you absolutely won't want to miss it. See you in the next one.